day, good afternoon, Miss Mushaida and everyone here. Today our group will present our topic, which is maximizing profit from two products. Okay, so this is our group members' names, and this is all of our topics. The first one is real world problem and calculus two concepts. The second one is mathematical modelings. The third one is the calculations, and the last is practical implications, limitations, and possible improvements. Okay, let's start by looking at a real-world business scenarios. Imagine a footwear company that produces two main products, let's say shoes and sandals. Now, if we act as the management team, of course we want to get the maximum profit from the two products. But how? If we set the price as high as we want to get maximum profit for one transactions, our customer will stop buying our product because it's too expensive. And of course, we cannot make the product price too cheap because our goal is maximum profits. On the other hand, both products are made in the same factory and share the same resources, such as machine capacities, the labor hours, and raw materials. So we cannot produce too much of one item which will hamper the productions of other items. Therefore, our main question is, what is the exact combinations of shoes and sandals that we should produce to reach the highest peak of profit? To solve these problems, single variable calculus is not enough. This is because real-world profit depends on multiple factors that affect each others. This is why we need tools from calculus too. So we use concept called multivariable functions. We will create a mathematical equations where profit is controlled by two independent variables at the same time. We will represent shoes as x and sandals as y at the same time, so the functions is p, x, y. These functions will create a three-dimensional surface plot. Visually, this graph look like a hill or mountains. Our team job is to find the exact coordinates of the highest peak of these profits. Now, how we find that profit peak mathematically? Here we use partial derivative. Partial derivative allow us to analyze the effect of one variable while keeping the other one fair and constant. When we find the partial derivative with respect to x, we are looking at how profit changes if we only change the productions of shoes, while the production of sandals remains constant. We do the exact same thing for the partial derivative with respect to y. The maximum profit happens when we find the local extrema and critical point. In calculus, the absolute condition to reach maximum profit is when all partial derivatives equal 0 at the same time. The intersections between two partial derivatives called the critical point. And later, our team will also use the second derivative test to prove that this critical point is truly our maximum profit. Now, after understanding the basic theory of multivariable functions and partial derivative, how do we actually build the real mathematical equations for the company? The mathematical modeling will be continued by my teammate, which is Wilson Darren. Thank you.
Thank you, Alianto Hosea. Now I will proceed to the next topic, which is mathematical modeling. Imagine you run a factory that produces two things at once, which is shoes and sandals. You want to maximize profit, but raw materials and machine hours are limited. So how many shoes and sandals should you actually produce to get the most profit possible? In this video, I will walk you through how multivariable calculus answers that question using a simple mathematical modeling. First, let's build the model. So let x be the number of shoes and y the number of sandals produced. These are our decision variables. We write profit as p of x and y equals r of x and y minus c of x and y. This means that profit equals revenue minus cost. Revenue, which is r of x and y, equals to p1x and plus p2y is simply price times quantity for its product. Next is the cost. C of x and y reflects the sale production resource, raw material, machine hours, whatever it may be, that both products draw on. and that is actually where the constraint comes in, which is ax plus by less than or equal to r. Shoes and sandals compete for the same limited resource, and their combined use can exceed the total capacity, which is r. Our goal is to find the point of x and y that maximize profit. To do that, we take the partial derivatives with respect to x and y and set them equal to 0. The point that satisfies both equations is called the critical point, our candidate for the optimal solution. But a critical point is not automatically a maximum. It could be a minimum or a saddle point. So we satisfy it using the second derivative test to the Hessian determinant. If D is positive and PSS is negative, the point is confirmed as a maximum. To make this clearer, let's recap what each symbol in the model represents. X and Y are the number of pairs of shoes and sandals, the variables we choose. P1 and P2 are the selling price per pair of shoes and sandals. R of X and Y is the total revenue. C of X and Y is the total production cost. And P of X and Y is the profit that we're trying to maximize. A, B, and R describe the resource constraint of how much resource each unit consumes and how much is available in total. Then the partial derivative with respect to x and y are used to find the critical point, and the Hessian test confirms that point is truly a maximum, not just any critical point. So that's all for my presentation. I will pass to my friend Gofani Felicia for the work example and calculations. Thank you.
Okay, so today I will explain the word example and also one calculation. So there's I will give two questions. For the first is mostly is about mathematical theory, and the second one will be the word example. Using how to maximize two product using multivariable derivative. Okay, so the first one, there's a given a function respect to x and y. Respect x and y. Here, to find how to get a critical point, we must derivative the function to respect to x and y using a partial derivative equal to 0. So each partial derivative like x and y will equal to 0 to find the critical point. So the first all for the variable x, we will derivative by partial derivative. So in here the function with minus 2x squared minus y squared plus 4x plus 6y plus 10. So if we derivative this respect to x, so in here the minus 2x squared become minus 4x, and 4x become 4, and the rest become 0. So after that, because it be equal to 0, so x be equal to 1. So for the variable y, so we partial derivative respect to y. So minus y squared become minus 2y, and plus 6y becomes 6. So y become to 3. So we already find the critical point is 1.3. And also we need to check again the verification. So the verification to know is this really the critical point is really a maximum point and is a local maximum. So we using a Hessian matrix. How to do a Hessian matrix? So just now the first derivative, the partial derivative, we derivative again to the second derivative. So this for us, the first derivative is minus 4x plus 4. So if we derivative again, it's become minus 4. And this for the variable y, the first derivative is minus 2y plus 6, and for the second derivative it become minus 2. After that, and also we also derivative the variable s to derivative and the second derivative to respect to y, and also the derivative, the first derivative the respect to y, and we partial derivative respect to x. Actually, although the different order, the answer will be the same. So if derivative the second derivative, the first derivative respect to x, if we derivative again the second respect to y, is become 0. Same also with here, the first derivative respect to y and with the second derivative respect to x become to 0. So it's actually same, and we will we make it to a matrix. So the formula is here, and we just substitute all the number, and after that we searching the determinants. So the determinant is 8. So since the determinant 8, which is 8 is more than 0, so the extremum is at 6. So it's so we can call there's a maximum point. So because, and also for the derivative of the second derivative of respect to s and x also is -4, which is less than 0. So it means that you can verify that critical point 1.3 is a local maximum. And also we move next to the second question. So the second question is we try into the word life example. So there's a factory that produce two product with sandals and shoes, and sandals be respected by x and shoes be respected by y. So there's a given a function of the product is p as y equal to 10 as y. So here there's a problem. There are strict budget constraint. So for each pair of sandals equals $2, and for the pants also is equal to $1. And also the total operational spending cap is $40. So if we make into equation is 2x plus y equal to 40. So in here that we need to find what the maximum, we can maximize the standard and to choose to maximize the output. So in here we use a Lagrange multipliers. Maybe someone will ask why don't use like directly substitution this equation to the function, because in Lagrange multipliers we can make the calculation make it easier rather than doing substitution. That substitution, like sometimes if the equation is like polynomials expression polynomials or like something like really tricky, like exponential, it will be really hard to substitution and really hard to be derivative. So we're using Lagrange multipliers. So here the Lagrange multipliers. So how we do it? So the first all we write again the function and the equation for the constraint, and also the constraint we make it as a function like this, 2x plus y minus 40. So it's like a 40 go to here. So we make a Lagrange function. So Lagrange function respect to three variables s, y, and lambda, with this just now function minus lambda times the function of the constraint. So if we substitution here, after that we partial derivative with three variables. So here the Lagrange function 10y minus 2y, if we derivative respect to s, is become respect to I and equal to 0, because in here we also need to search the critical point to find the how many products to get the maximized output. So 0 to 10y minus 2 lambda, 2y equal to 2 lambda, lambda equal to 5y. Same here, the same way. So lambda respect to partial derivative respect to y is become 10s minus lambda, and 10 equal to 10s minus lambda, and lambda is equal to 10s. And also for the next, the third variable is lambda. We derivative it again. So from this function into here is to 40 minus 2s minus y equal to 0. So we find 40 equal to s plus y. So in here we do substitution lambda with the lambda. So lambda equal to lambda, 5y equal 10s, so y is equal to 2s. After that, this equation we substitute to here. Substitute here is become like this: 40 equal to s plus y. We change to 2s, so we become 40 equal to 4s, and s become 10. Here we redefine the critical point is 10 of 10.20. And here there's a lambda we also can substitute the y equation. This 5 times 20 is equal to 100. Actually 100 in here it has a something advantage of using a Lagrange substitution, Lagrange multipliers, that we can know the schedule price. Here that it can help for the production management to see what happen if they increase the spending cap. If like $41, what happen will happen. You hear that when I do a calculation, if become 41 is the product can increase the cost. How many products you can increase? Like around 100 products. Here by the lambda we can already know this lambda is also 100, so it is have a accuracy to know how if we adding some cost, like how many production that can be increased. So for the verification, this one a little bit different. We use a border Hessian matrix, so it's 3 times 3. Here same method like before. Just now the function of the first derivative with derivative again, and also the y also with derivative again, and also same just now the derivative respect to s we derivative here to respect to y, same with the opposite with the other derivative. And also we add something with the gsy. We also derivative just now the function of constant with derivative respect to x is equal to 0, and we first derivative again respect to y is equal to 1. So we make it in one matrix, and here this is the how we make it. So if we substitute all answers, the determinant is become 40. In here there's a special. We no need to search there's not like here we need to search the derivative of the second derivative again, because in here the border Hessian, if already find the dependent is equal to 40 and is more than 40, we can directly conclude this is the local maximum, and the critical point of just now 10 or 20 is the most optimal maximum of the product that we to optimal respect just now this constraint. So this is the most optimal of how many product they can be produced.
Hi, my name is Ang Yingjie and my student ID is CST2109078. So now I'm presenting the strategic production allocation for our footwear factory, focusing on how we maximize our total output of sandals and shoes under a fixed operational budget. Using the Lagrange multiplier method, we determine that to hit peak factory output given our $40 cost cap, our absolute mathematically optimal target is to manufacture exactly 10 pairs of sandals and 20 pairs of shoes. This precise combination ensures we optimize our assembly lines and materials without overspending. So, let's explore the practical business implications. In solving our optimization problem, our Lagrange multiplier, lambda, yielded a value of 100. Incorporate economics. This is our shadow price, which represents the marginal value of our budget. This signals to management that if we invest just one additional dollar into the factory's production budget, increase it from $40 to $41, our maximum combined manufacturing capacity will expand by 100 additional production units. This metric is crucial for forecasting future scaling costs. However, as managers, we must address the limitations of this current model. First, it assumes a static cost environment where the unit cost of sandals remains fixed at $2 and shoes at $1, overlooking market inflation or bulk leather and rubber discounts. Second, Our interaction function tracks the pairing of sandals and shoes as fluid, completely ignoring physical factory storage limitations, separate machinery's breakdowns, or specialized labor shifts. To bridge this gap and turn this into an actionable corporate blueprint, we propose two vital improvements. First, we must integrate dynamic pricing models to adjust for seasonal material cost fluctuations. Second, we should implement the Karuskun-Tucker inequality conditions to factor in real-world capacity thresholds, warehouse space, and daily labor caps. Transitioning to this advanced model will elevate our basic calculation into a high resilient decision-making framework. This is the end of our presentation. Thank you.